Okay, good morning, everyone. It's time to start. So again, just a reminder, please take some time to look at our Kaggle computation task, and you should be able to see the invitation link. You can walk through the content, the challenge, and also the way you're going to do this Kaggle computation. And then you can make a decision if you want to do this competitive project, or you want to form a team to do something exploratory project. And yeah, that's it. So let us continue with the ensemble learning. So in the last lecture, we started to talk about ensemble learning, a very classical and popular machine learning strategy. So ensemble learning does not mean one specific algorithm. It actually contains a collection of models and algorithms. Their idea can be summarized. Okay, I want to assemble a collection of base learners to further improve the performance. Right? So the most commonly used strategy for ensemble learning includes boosting and bagging. Okay? So in the last lecture, we mainly talked about boosting. And the idea of boosting, of course, boosting also has a lot of instances. Like we're gonna focus, we mainly focus on AWS. So, but in general, boosting aims to assemble a set of weak classifiers or weak learners, and into a much powerful, much stronger classifier. That's the idea of boosting. So the essential boosting method is to repeatedly reweight the training examples. Based on those newly weighted training examples, we train a classifier. Of course, it's a weak classifier, which can correct the mistakes made by the previous classifiers. And finally, we combine those set of weak classifiers and to produce the final output. Right? So the most well-known and powerful, perhaps successful boosting algorithm is called AdaBoost. Right? So we have walked through the details of AdaBoost in the last lecture. So here we're gonna review them. Right? So here is the algorithm steps, which I believe is detailed enough for everyone to implement your own AdaBoost. So suppose we're given a training set with m training examples, and suppose we're doing classification task. So each instance is labeled with either -1 or +1. So at the beginning, we're gonna assign the same weight for every training example, right? Which is 1 over m. So we use this d to denote the weights of the training examples. At the beginning, they are all the same, all equal, right? And their summation must be 1. Right? This is required. And then we go through like big T iterations. Right? So here you have to choose this parameter big T. And of course, for one application, maybe 10, big T equals to 10 is enough. For another, might be 100. It really depends on applications. kind of like a parameter you need to tune according to your problem. So inside each iteration, we're going to sequentially run those iterations. So inside each iteration, based on the current sample weights, we're going to learn the classifier h of t. Well, this is a weight classifier, and we expect that its weighted classification error is better than chance, meaning that errors will be slightly less than 50%. Okay? And then based on this weighted classification error, which is weighted training error, we have given the definition in the last lecture. In one sentence, the weighted error is computed as the summation of the weights of those incorrectly classified examples in the training data. Okay? So now, based on this weighted error, we can compute the vote, which reflects the importance of this weight classifier in the final stage. So it's computed like that: 1 over epsilon t over epsilon t equal logarithm take half. So because epsilon t is better than chance, right? That means epsilon t is less than 50, 0.5. So this number is always positive. And then using this RT, we then update the values of weights for the training examples. So we just use our learn classifier ht to predict label of every training example, right? And then we update each example I its weight accordingly. Right? So here's the rule, right? So if your prediction is correct, what's the production of the ground truth label and the predicted label? It's always 1, right? So either you both predicted it as 1, right, which is correct, or both predicted as negative 1, but we multiply two predictions together, it ends up with the positive 1, right? So now you multiply this exponential term, e to the power of minus RT times 1, meaning that you are multiplying a factor which is less than 1, right? So remember, e to the power of 0 is 1, right? So if e to the power of a positive or negative number is less than 1. So we're actually reducing the weight. When you have correctly, you are able to use ht to correctly predict xi. On the other hand, what if you make a wrong prediction? What's the product of this? Yeah, it's minus 1, right? Remember, our label is either 1 or minus 1. So you're gonna have a different values, right? Yi is 1, you'll make a wrong prediction, so your prediction was minus 1, right? It's minus 1. Or Yi is minus 1, you'll make a wrong prediction to be positive, so its product is always minus 1, right? So minus, you end up with being positive. So you're multiplying a factor which is gonna be bigger than 1. Right? That means you're gonna promote the importance of this incorrectly classified example. Why should we do this? Because we want to promote the importance of the examples which are incorrectly classified so that we can leave them for the next round of iteration. So we expect that our next round classifier can correct such a mistake. Meanwhile, if you make a correct prediction, that means, okay, now that I can correctly classify this, not that important, I'm going to demote the importance. And finally, we need to normalize all those updated weights to ensure that their summation is 1, right? That's how we compute. That's why actually we compute the ZT, right? Easy way would be like compute ZT would be first, okay, before normalization, I just multiply the original weight. I mean, the weight comes from the previous iteration with the corresponding factor, right? And then you just add all those together across the training examples, which will be ZT, right? And now you've got the normalized sample weights for the next iteration. And then we proceed to the next iteration, right? Based on the updated sample weights, we train a new classifier, which we expect whose weighted error is still better than chance, and then we compute its vote, update weights again, and repeat this procedure until all the big T And after this loop is done, we will collect a big T weak classifiers. Right? And now the final stage will be assemble them together. How do we assemble that? AWS uses a very simple strategy, which is to do a linear combination. Remember, for each iteration, we have computed the vote for that weight classifier alpha T, right, according to the weighted training error. So in the final stage, whenever we make a prediction for a new example, we just make a prediction with each individual classifier, and their prediction will have its own vote alpha T, right? And now we just compute the total votes for positive prediction and total votes for negative prediction, and use the one who wins the convert. Right? So that's why we use this formula, because positive one, all the positive votes are added together, and if it's negative one, they're gonna be subtracted by the total votes of negative prediction, and you can decide the final winner according to the sign of this summation. So I've discussed about this in the last lecture. So here is this whole algorithm framework. Any question about that? Because this is really important. In your homework too, you need to follow this pseudocode to implement your data boost based on decision styles.
How do we select HFT? Like it just says find a classifier. How do we?
Yeah, that is determined by which base classifier we're going to use. For example, the most commonly used base classifier of AWS will be decision style, meaning that you're just training a one-level decision tree, right? And then when you learn decision tree, you follow ID3 to track the information gain or GD index gain, whatever. But of course, you can use any other classifiers as the base learner. Any other question?
Or we can talk at any point about, like, if I got the highest value you can get and like the lowest value you can get, if you get like close to 0 in that sign function, then maybe you're kind of in between the two.
Oh, yeah. That's a good question. That's actually still the time problem. If there's a tie, meaning that it's simply 0, right? So actually, you got positive prediction and negative prediction to have the same total vote, and how do we decide, right? I mean, if you don't have any preference according to your own experience, you might choose either of them. There's no guarantee which one's better or not. But you have say your own experience saying that okay, I would like to prefer positive, and then you choose positive. There's no one answer for this. This really depends on the problem. Yeah, this is actually some kind of user freedom to decide. Any other question? Okay, great. So now let us go back to the for example we have shown. Right? So our weight classifiers are simply the axis parallel lines, right? Either vertical or horizontal, right? So we just run our data boost for 3 iterations. We end up with 3 weight classifiers, and we computed the corresponding votes, right? Alpha 1, alpha 2, alpha 3. And then in the final stage, we're going to do a linear combination of those weight classifiers together. And interestingly, although all the 3 classifiers are very simple, right? And when we combine them together, we find that the decision boundary is much more complex, right? So that actually showcases how the boosted classifier get promoted upon those weight classifiers. And you can see that each individual classifier cannot well fit the trained data, right? They always present this, but if you can smartly combine them together, we got 0 training error. So before we talk about some kind of common observations about data boost's behavior, I want to give a few hints in implementation with decision trees, because in your homework too, you're gonna implement this with decision trees, right? So there are some questions, or someone might feel confused about, like, I have weights on my training examples, right? And now how do I construct a tree? And how do those weights affect the training result, right? So different weights end up with different trees. The answer is yes, right? So the computational procedure is exactly the same. So don't worry, actually. And so the problem is, I mean, to create this tree, right? Imagine we're running our ID3, right? The K step will be compute some information gain, right? Either based on entropy or majority error or gene index. And you select attribute, you partition the data sets, you create new branches, right? And then you select next attributes, partition, and go on until you reach the leaves. That's the whole procedure. And then the key step will be to compute the information gain for the weighted examples in the current set. How can we compute it? And it's all.
Couldn't we just do it the same way we did when we had a missing attribute value where we attach weights to the different values?
Yes, exactly. Right? That's something I want to emphasize. Right? Don't forget, we actually have talked about how to do that. Right? Just will those examples as fractional examples. Right? So previously, when we talk about a very important strategy to incorporate the missing incomplete training examples, right? Suppose you got one training example whose one attribute is missing, right? And how do we deal with that? Okay. So I think a good strategy will be, okay, I'm gonna break this one example into 3 or 4 fractional examples, right? Where each example, the missing attribute is filled with a particular value, right? But the fraction is determined by how likely you believe this attribute will take that value. And then we showcase how to compute it. And here, to compute the information gain based on weighted examples, we can follow exactly the same way, right? So just to give a toy example to show the idea, right? So this is just 5 examples. Suppose you're running your boost on this 5 examples, right? So each step, of course, you're gonna create the weight classifier, right? Each iteration. So at the beginning, you're gonna assign equal weight for each example, 1, 2, 3, 4, 5, right? So the first 2 are negative, and the next 3 are positive, right? So their weights are just all 1 over 5, right? 1/5. So then to compute information gain, we need to compute entropy, right? How do we compute entropy? We need to know what is the positive probability, what is negative probability, right? So what is a positive probability? Or positive proportion? You just add up the sample weights for all the positive examples, right? So you have p positive equals to 1/5, 1/5, 1/5, add together 3/5. And p negative will be summation of the weights of the remaining examples. So it's 2/5. Remember, we require that the summation of the total weights is always 1, right? So actually, you don't need to like multiply it with the count and divide it by total number of counts. Just add up all the weights with the same example. You even don't need to do the normalization because the total normalization is 1. And once you get this p positive, p minus, you just calculate the entropy accordingly. Now suppose like you use this set of weights to create a decision tree, right? Decision stump, and you got some error, right? You got some weighted error, and you compute votes, and in the next iteration you're gonna update your weights, right? Suppose now the weights of those examples are D2, right? They have been changed significantly, and now we want to create a new decision tree based on this weighted examples, right? The example is the same, but the weights are changing. How can we do that? Again, I mean, we follow the same algorithm. We need to compute an information gain, right? And we need to compute entropy. So the problem is how to compute entropy. To compute entropy, we need to know the P positive and P negative. So now, okay, tell me what is P positive, what is P negative?
P positive is 5/8. You just add up the fractions.
Yeah, exactly, right? So P positive, you just look at the weights for all the positive examples, right? You just add them up. So it's 1 over 8, 3 over 8, 1 over 8, right? Add them together, 5 over 8. And P negative, what is? You just look at summation of the weights for the next example, 3 over 8. And now we compute the entropy. So you can see that because of the changes of the weights in each iteration, right? You calculate different entropy, and you calculate different entropy of the splitted success, you end up with different information gain. That means you might have selected different attributes to split the data, and accordingly you create the tree, you grow the tree with different branches. Right? So end up with different trees. Any questions so far? So hopefully this will address the potential questions during the implementation. But yeah. Okay. So there are many theoretical results about data boosting. So here we just want to introduce one, right, about the training error, and showing that how easily data boost can well fit the training data. So here is the theory. Suppose we're going to run data boost for big T rounds, and for each round we have our training error, which is weighted training error, half subtracted by diameter. Diameter is small, that's why we assume we have a weight classifier. So the error is kind of not too much smaller than 50%. And then suppose for all possible T, for all possible iterations, we have a strict non-zero lower bound of the diameters. So assuming non-zero lower bound for all T. So here just I need to point it out. This could happen in many applications, but this is still a little bit strong assumption, and it does not guarantee to always be the case in practice. So that means if you make the number of iterations in theory to be infinite, then this lower bound might be simply 0. So just be aware of that, and don't try to apply these theorems to every problem you can see. You need to be aware of the subtleties here. Okay, but here let us just assume, okay, for whatever T, right, whatever choice big T, and whatever specific iteration, right, if you just collect all this guarantee together, you have a strict, we have a lower bound strictly bigger than 0. And then we can show that the training error at the final stage, meaning you have assembled all the weight classifiers after big iterations, this training error is upper bounded by e to the power of minus 2 gamma squared dt. So what can we conclude from this result? Any thought? No idea? Any thought? Any guess or whatever? So this is a exponential function, right? If you look at how the training error varies along with the total number of iterations, right? So you can view that this upper bound decreases exponentially along with the number of iterations, right? So that means it, the training error drops exponentially. Right? that's very impressive. I mean, the more iterations you run, along with more and more iterations, it can quickly drop to 0. Of course, you have to assume that this lower bound gamma is non-negative. If gamma is 0, then you don't have, this bound doesn't have any meaning, right? But here, let us assume gamma is bigger than 0. You can see that as t increases, like big T to increase, your training error drops really, really quickly. And this proof is not hard. It's actually pretty simple. Just the application of several common use inequalities. So I will put this proof in our course web page. If you have time and if you're interested, you can take a look at the proof. And what does this theory tell us? It just tells us in many practical applications, if you choose itables, right, as long as we run enough number of iterations, we can perfectly fit the training data. That's a kind of typical property of itables. However, this might not be good, right? This might not be a good property. We have discussed before, right? Remember, we know that decision tree, if you don't control the size, don't control the growth, it tends to overfit training data, right? And itables now tends to overfit the training data as well, right? And the speed to overfit the training data is so fast, right? Exponentially, right? And it seems pretty bad. But there are some kind of exception for itables. You see that many practical applications, itables does not suffer from overfitting at all. That's an open problem. But here, I just want to give you a concrete example showing how training error decays with itables iterations. Right? So here is just the running iterations of itables on some practical data set. This is a well-known figure. Right? So you can see that along with more and more iterations, meaning you are adding more and more weight classifiers, your total training error grows in this respect. And in many applications, you see the training error just goes down to 0. So this just showcases how fast the training error can be decreased during the training of itables. And at the same time, if you look at the weighted error of each individual classifier, things kind of like changed. So you see that in general, the individual classifiers, their weighted error tends to increase, meaning that if you train your weight classifier obtained in a later stage, they tend to perform worse than the weight classifiers obtained in the earlier stages. That's also the practical observations. You might feel a little bit strange, but here I'll just give you an intuition why. So remember, we're trying to reweight the training examples, right? And every time when we misclassify an example, we're gonna increase the weight, right? We're gonna increase its importance, and for those correctly classified examples, we're gonna downweight them. So you can imagine at the beginning, your training weight classifiers, it is easier to predict or fit those easy to train examples, those easy examples. And in later stage, you have to face more and more difficult examples, hard to classify, hard to fit. Because easy problems will be first to solve, so their examples, their weights are kind of lower and lower. Right? And in the later stage, all those largely weighted examples are hard examples. So remember, you are training a weight classifier to predict or to fit those examples. Of course, it's kind of hard. Any questions so far? Okay, so let us talk about overfitting issue. Right? So as we have discussed before, right, we don't like overfitting. Right? This is a typical learning behaviors for for a machine learning model, right? So you don't control the fitting of your model, right? So what will happen when you run more and more iterations, right? You can keep decreasing your training error, but at some point, some turning point, your test error starts to go up. That's something we don't want. Right? We want to stop our training at this critical point. Right? The typical example is decision tree. You have shown a similar graph, right, for real world applications, right? So these behaviors or this kind of learning curves apply to almost all the machine learning classifiers. If you train a neural network, deep neural network, you will observe the same behavior as well. That's why an important trait in neural network is called early stopping. Early stopping is just a technique trying to detect this point accurately. So if this happens to AWS, that's not good, right? We don't want to happen, right? And there's something, however, there's something like AWS does not behave similar to other common used machine learning models, right? So this is what we can observe in practice. So again, this blue curve shows the training error. How does the training error vary along with more and more iterations? Meaning more and more weight classifiers are added, right? And this red curve shows the performance of the test error. So remember, test error is performed, is calculated on different test sets, right? So that's that's surprising, right? So in many practical applications, what we can observe is that okay, even your training error goes down to 0, your test error can still keep decreasing or being stable. It won't go down. It won't go up. So it seems that okay, the AWS can well fit to the training data, even perfectly fit to the noises in training data. However, the noises does not produce a bad effect or is not able to mislead the AWS learner. At the same time, AWS can still keep doing well in generalization. So why does this happen? There's still an open problem. So but a long time ago, right, the inventor of AWS, they give some possible explanation. But this is typical behaviors of AWS, just to just let you to realize this is the difference of AWS from all the other machine learning approaches. For all the other machine learning approaches, you often see this. It's very often to see this. But AWS, the learning behavior is like that. So you're gonna test this on your own application in the homework too. You will see the same behavior. But it does not guarantee like training error is always goes to 0. Right? You might see like training error becomes very small and then stable. That's actually dependent on the data nature. Maybe your number of features are not not enough to give a 0 training error. But you still see that okay, even your training error keeps decreasing until to be very small. Your test error doesn't go up. Okay. So now we have wrapped up the boosting and AWS. Right? To give you a brief summary, AWS is very common use, very successful boosting learning algorithm. What's good about it? Simple, fast, and only to tune one additional parameters, limiting the number of total iterations. And it is general enough. You can apply it with any weak learning algorithm. But of course, there is no free lunch, right? AWS has its disadvantages. Here are the keywords. Right? So the performance depends on data set and the choice of weak learners. To make AWS work, you really have able to choose the right weak learner. If the weak learners are too complex, meaning that they're kind of like strong, it will fulfill. If weak learners are too weak, meaning that okay, it is the same performance with random tests, it will fail as well. Right? So the choice of the weak learners is really important. And empirical evidence proves that okay, AWS is better to be combined with decision stumps. We actually talked about it a few times. Right? Decision stump is just a decision tree with one level, meaning that every time you just select one attribute to split data, then you create lymph nodes, a stump. So in our homework, you will also be asked to implement AWS with decision stumps. Okay, any question so far regarding boosting AWS? Is everyone comfortable? Okay, great. So now let us talk about another very important ensemble learning strategy, which is called bagging. And we're going to talk about the general bagging framework, and then we'll talk about a better version, which is called random forest. Maybe you have heard it many times. Random forest is very, very popular and very commonly used. Okay, so what is bagging? So in general, bagging is another ensemble learning algorithm that combines output of multiple classifiers. Right? And different from boosting, we're not going to require our base learners to be weak. We actually require the base learners to be strong. Even you can, you are encouraged to overfit the data. And then in practice, bagging often tends to be robust, and we'll justify why. And for example, the winner of this 1 million Netflix prize in 2009 was John Ensemble. So if you take a look at the reports in Kaggle competition classes, many top rank solutions they involve some bagging strategy. So here is the bagging framework. So it's really simple, but it works surprisingly well. Right? So first, the bagging is short for bootstrap aggregating. But as we all know, bagging itself, this word itself, although it's an abbreviation, it also explains the essential idea here. So bagging actually means that okay, you put a bunch of classifiers into a bag, and then you just average your predictions made by the classifiers in the bag. Okay, so let us look at the whole framework, right? So suppose we're given a training set with m examples, right? The same data setting, and then we also do big peak iterations. Of course, we need to set up the big peak, right? And then inside each iteration, we're going to draw a new data set from the original data set. And suppose the size of new data set is chosen to be m prime. Right? M prime is usually less than or equal to m. And how do we create this new data set? We just draw each example uniformly with replacement from the original data set. So what does uniform with replacement mean?
So you same chance of getting every sample, but you can get the same one twice also.
Yes, exactly right. With replacement means that okay, once I draw a sample from the set, right, I do not pick out a sample from the origin set. I can place them back, and then I draw it again with the same chance. That means one sample can be drawn twice. That means in your newly generated data set, then they might contain duplicated examples. So let me use some concrete example to highlight this point. Right? So if you choose m prime equals to m, then when you sample a new set of examples, this sample is called a bootstrap sample. So bootstrap is a term in statistics, just means resampling from some collected data set. So for example, your original data set consists of 5 examples, x1 to x5, right? And your m is 5, and now I choose m prime to be 5. I'm going to generate 5 new examples from this original data set. So remember, we're doing uniform sampling with replacement, meaning that, okay, when I sample x1, I will not take x1 out from the original data set. I will put it back, and then I do the sampling. So x1 in the next time still has the chance of 1 over 5 to be sampled. So here we can see the result, right? In the first bootstrap sample, right? The first sample, x1, note that we do not take x1 out. Right? x1 is still there. So in the next time, we still sample x1. And third time, maybe x2, fourth time, maybe x5, x4, and fifth time, x2 is sampled again.
Is M prime just selected randomly each time?
No, it is usually set by users. So, like you can choose M prime to be 1/10 of the size of the original data, or you can choose M prime equals to M. For random forest, well, we just use M prime to be M. And in the second bootstrap sample, right, in the second sampling procedure, you might have the first two samples both are x2, right? And then x3, x4, x5, and the third trial, you might have x1, x3, x4, x4, x5, x5, x4, right? So here, just use those duplicated examples to emphasize the possibility that you might have a sample, the same example multiple times. So that's the meaning of the uniform with replacement. Okay, so once you have generated a new data set of size M prime, I'm going to use these M prime examples to train a classifier, which this can be any classifier, and which we denote by CI. Okay. So once you run all the big T iterations, you've got big T classifiers, right? And then you just aggregate them together. How do you aggregate them? If you're doing classification, you just vote the predictions of each classifier. And if you're doing regression, just average their prediction. That's it. But remember, the big difference from the AWS is that, okay, we do not put extra weight for each classifier. Each classifier are considered equally important. Like suppose you are 10, you have 10 classifiers. For a particular example, 7 predicts positive, 3 predicts negative, then you have a vote for positive 7 and the vote for negative 3. That's it. You don't multiply with different weights for each individual classifiers. Okay. So this is a backend strategy. So any questions so far about this framework? And also, we do not reweight training examples. Yeah, this is something, another thing I want to highlight. So we do not recalculate the weights for different examples. Every example is the same, as equally important. We do not update the weights. The difference is that, okay, every iteration we're gonna draw a different data subset, right? But because doing uniform with replacement, there are still possibility that different sets are overlapping, or partly overlapping. So the benefit of this, one benefit of this is that you actually can conduct these big T iterations totally in parallel, right? Because we do not, like iteration T, the training procedure does not depend on the previous result. Right? You just do the uniform sampling with placement on the original data set. It doesn't depend on all previous running results. Right? And based on the new data set, you train classifier. That's a benefit. It's just not sequential. You can, it's not sequential in nature, so you can do it in parallel. Okay, so tagging in general is a method to learning multiple versions of one classifier and using this to get an aggregated prediction. Right? So if you're doing regression, you just average over the predictions made by each learned classifier or regressor. If you're doing classification, just count both. Same thing. this is the same thing as we just discussed, right? So those multiple versions of the predictors are constructed by making bootstrap replicas of the learning setting using the training set, right? That's basically telling us how to regenerate a data set from the original data set. And although it seems like surprisingly simple, right? And many tests are real and simulated data on both classification and regression tasks show that bagging can give substantial gains in accuracy. And why? Why does bagging work so well, right? What is the intuition? So it is just, okay, every time I just resample the training examples, and based on which we train a classifier, and the classifier can be as strong as we want, right? Like if you want to use decision tree, you just grow the decision tree as large as possible. And if suppose you're doing this for 10 iterations, you got 10 big decision trees, right? And during the prediction, you just average the results. So why it is working so well, right? Any thought? Okay. So here's just to give a graphical illustration. You've got quite a few different trees, right? You just do the average, but here it's just for the regression case for the classification, just both. So before we explain why it works, I just want to ask your thought, right? What is your intuition why this strategy works?
You're just averaging out the error. So most of them are probably going to not have errors. Your average should be better than maybe one will have error.
Yeah. Any other thought?
I think this is removing variance by averaging over a bunch. Basically, the chance that you happen to just get a weird tree is low.
Yeah, that's excellent. Actually, you're kind of supplementing the idea that you mentioned. Any other thought? Yeah, I think both of you are seeing the right points. And actually, we're going to justify this with some mathematical analysis. So, intuitively, right, if you have more predictors, right, to do the average, as suggest we can average the noises, so we can get more reliable, robust result, right? And also, when you do the average, okay, if you do an average, you're actually reducing the variances. But now, how do we justify there? Indeed, reducing the variances. So we're going to use some kind of analysis, of course, which are making some kind of assumptions, which does not extend to all the general cases, but from which we can review. It can review the structure inside the arrow, and from which we can see which component does the bagging strategy reduces. Okay. So we denote our training data set by big D, and based on D, we can learn a predictor H. So this analysis applies to any machine learning model, not only to bagging. So suppose we have a learning algorithm, right? So just learn a predictor. It might be a decision tree, it might be whatever else, maybe a neural network. And our target function, or the ground truth, is that. Right? So now, we're given a new test example, X star. So here we assume, okay, the test example is fixed. Right? We're not talking about average over all possible test examples, just one example fixed. Right? And suppose we're doing regression. This is kind of a little weird because most cases we're doing classification, but here, just for convenience, we'll use the case of regression. We're predicting continuous values. So now we want to say what is the square error, meaning that the square difference between your prediction, learned by a model, right, based on D, and the ground truth prediction. And we're going to consider on average what is the square error. On average means that, okay, it is take expectation with respect to the distribution of the training data. So you can imagine, roughly speaking, now that rigorously speaking, you're collecting training data many times, infinite times. Each time you got H, right? And you make prediction, you have error, you just average all possible errors. The same, okay, we have taken into account the underlying data distribution which produces or provides the training data. So we want to look at what besides this expected square error. Okay. To do that, let's do a little bit trick. Right? So we know that inside the square we can minus a constant and plus a constant. Right? So these two terms are cancelled, so you still have the original square. Right? So we subtract x squared by this expectation of the prediction, and plus the expectation of prediction, and then subtracted by h of x star. Right? So what does that mean? What does this expectation mean? Any thought? Any thought? H is our learn classifier, right? Based on data set D, right? So we take expectation, meaning that, okay, you're gonna take all possible training set, right? For each particular training set, you learn H, you make a prediction over X star. Right? H is dependent on the training set. Now you take expectations. It's just the average prediction when you train a classifier on all possible data sets. Right? Any question? Right? H here can be viewed as a random variable. Right? It depends on the training data, right? But the training data itself is a random variable. So you're essentially taking expectation of your learned predictor across all possible training data sets. So now you subtract this and add this. Now you take the square, right? We can expand the square, right? According to this term and this term, right? And term 1, this, term 2, this, and you add them together, you take square, you end up with 3 terms if you expand the square, right? That's the square of the first term, square of x star, subtracted by this expectation of the prediction, right? Plus square of this term, right? Expectation of hx star, subtracted by hx star, take square, right? And the cross term. The cross term will be this one multiplied this one. Of course, it appeared twice, so multiply this twice. And remember, outside you have expectation over data distribution, so you put expectation over data outside for each of these 3 terms. So this is just a common use way to expand the square summation. So now we can observe that, in fact, this cross term is simply 0. Why? Why is this simply 0?
Because the expected value of all the possible hypothesis is the target function. So the first term.
This one, this term?
Yeah.
I'm afraid not. So because you cannot assume your algorithm is unbiased, meaning that it can always on average can find the right hypothesis, right? You cannot assume your learning always is that powerful. So but following your thought, right? So let us look at the first term. First, f of x star, the ground truth prediction theory is constant. Has nothing randomness inside that. And this part, you have already taken expectation over the learned So this is now random as well. So that means the first term is actually constant. We can move it out into the expectation, right? And the remaining thing is calculate the expectation of this term. The expectation of this term, what is that? First, the first term inside this parenthesis is a constant, right? Because you have already taken expectation over the learner about this prediction, right? And you can move the expectation inside. You got another expectation, which is the same expectation as here. That's where we get 0, the second term. Any question regarding this? It's just applying what we have reviewed previously, right? What's the definition of expectation? So now, once we have a, oh, by the way, I just want to confirm, is everyone okay with that? Everyone's fine?
So it's not the first thing being multiplied by 0.
Yeah, that's the second. So the first term, let me repeat again. F of x star is a ground truth prediction, ground truth label. It is constant. Given x star is fixed, right? It is constant. And there's nothing random there. And this expectation, we know that h depends on the data d, right? We have already taken expectation. So this one will be the mean, right? It's already constant as well. So this term, their first term, right, is actually constant. So when you take expectation, you can move this constant out. You only apply expectation over the second term, the terms in the parentheses, second parentheses. But you know that this term again is constant, so when you take expectation outside, you can move the expectation inside to this h of x star again. So this expectation is the same as this expectation. With respect to data, so it's simply 0. So yeah, I mean, if you're still a little bit confused, don't worry. Just after class, you can do it by yourself. In the paper, you'll find it just according to the definition. So now, we'll only leave 2 terms here. Right? The expectation of this square and the expectation of this square. Right? This one and this one, I just copy it here. And now, as we mentioned before, right? Fx star constant, expectation of your learned model's prediction with respect to all the data distribution, with respect to all the training set is constant as well. So you can get rid of this expectation. So you got the first term. And second term, according to the definition, is essentially the variance. This is the variance. Remember, variance is the expectation of the square difference between the random variable and random variable's expectation. So this is essentially the variance of your prediction of your learned model across all possible training sets. So what does this result imply, right? So the expected error, right, across all possible training sets, essentially can be decomposed as 2 terms. The first term we usually refer to as bias. And the second term actually has nothing to do with the ground truth. The ground truth is the ground truth prediction at start. Has nothing to do with the ground truth. It only depends on the learning algorithm, right? It is the variance of your model's own prediction across all kinds of training sets. So you can imagine that you might have like a very simple algorithm where for every possible training set, they're going to keep 1. They want to return exactly the same model. Then your variance is simply 0, right? But you might have a super complex, super sensitive algorithm, right? And for different training set, you might end up with very different model parameters, model structures with very different predictions. Then your variance will be large, right? So actually, this second term reflects the stableness or robustness of your training procedure. So, in practice, I mean, numerous applications have shown that the performance of your learning algorithm is always a kind of trade-off between the bias and the variance. And the more complex, more flexible, expressive your model is, the more likely you're going to have a small bias, yet with large variance. On the other hand, if your model is simple, is robust, then you're going to have a large bias, but smaller variance. This is most often cases, although I'm not saying it will be guaranteed to be like that, but most observations have revealed this behavior, meaning that you always have a bias and a variance. And it's very hard to simultaneously reduce bias and variance. Okay, so why does we have such kind of trade-off, right? So here I just give you some information. So you can imagine that if you have a super powerful, super flexible algorithm, like neural network, like tree, for every training data, right, we're trying to do my best to fit the training data. So that means for every training data, your training error, you can imagine extreme cases is kind of close to zero, right? And then on average, because the test point is also sampled from the same distribution that generates the training data, your average could be the average of the prediction on all possible models could be quite close to the ground truth. That means that you have a small bias. But what's the bad side, right? What's the disadvantage? Because your algorithm, your model is so sensitive to the training data, because it's kind of guaranteed. Every time we switch the data, you're gonna have almost zero training error. A slightly change of the training data is easy to make your model change dramatically, right? Because they want to adapt to this slight change. At the same time, they want to keep the wild fate of the remaining examples. That means their model parameters and model structures is very sensitive to the training data, meaning that their predictions depends on the training data, can vary a lot. So those complex models often have large variance. On the other hand, if you have a simple model, right, like the model we're going to discuss after the ensemble learning, which is called linear models, they're essentially finding a line to separate points, positive points, negative points, right? If the point is very far away from the decision boundary, you change them, you modify them, it actually does not change the whole boundary. That means your model doesn't change. So you have a small variance. Your slight change of the data set won't cause a dramatic change of model. However, because the learning algorithm is simple, you cannot expect it can perfectly fit the training data. That means it often underfits the training data. Then it's likely to have a large bias. So you can see there's no free lunch, right? You have more powerful models, you have a bigger hypothesis space, you have a flexible learning mechanism. You tend to well fit the training data every time, so on average you have a small bias, but because you're sensitive to the data, you have a large bias. If you choose to run a simple algorithm, right, less expressive model, right, you cannot fit the training data very well, right? So you have a large bias. Benefit is that, okay, your trained model is stable, right? It's not that sensitive, or it's not that easily influenced by the change of the training data. So very small. Does it make sense? Okay. So decision tree is some kind of expressive classifier, right? If you don't control the growth, you don't control the tree size, and you want to grow it as large as possible, it always tries its best to perfect fit to the training data, right? So obviously, decision tree tends to overfit the training data you have. It has a small bias on average, but has a large variance. Imagine that you slightly modify training examples. You delete a few of them, or add a few more, right? And then you might have like some change of the attributes to partition data set and the branch trees and so on. Right? So typically, decision trees have a small bias, a lot of variance. And then here is where bagging can help. Remember, bagging is trying to learn many decision trees together, right? Or any other classifiers. Here we just use decision tree as an example. And then we do the average of those decision trees prediction. So know that suppose you have a bunch of random variables, they are identically distributed. So you take the average of those random variables. On average, the mean won't change. That means the bias term after using bagging strategy does not change, or is very close to using a single decision tree. But how about the variance? How about the variance? I suppose you have like 10 random variables, they follow the same distribution, right? Suppose, I mean, in the extreme case, those random variables are independent. Now you take the average of this random variable. Of course, it's another random variable. How does the variance of this new random variable change? It reduces a lot, right? So, yeah, maybe it's better to write it down, right? So, yeah, I write here just because it's better to be recorded by the video. So, please bear with me if you see here, right? So, and suppose you train a single decision tree, right? H. Well, we know that the bias is small, but their variance is large, because decision tree is kind of sensitive to the training set, right? And how bagging helps, right? Bagging is trying to train like 10 decision trees. H1, H2, H10, right? And we assume an ideal case where all those decision trees are independent of each other and they follow the same distribution. So we know that when we make a final prediction, right? You'll just average the prediction by all these decision trees, right? You take the expectation, right? It's the same as the expectation of each single variable, right? That's the property of the random variables. But how about the variance? So now your variance becomes the average of this 10 decision trees prediction. So your variance now becomes the average of this summation, right? Right? So, I mean, the basic statistics tells us if all these 10 predictors, the predictions, follows the same distribution and independent of each other, this variance can be only 1 over square root of 10 of this variance for each single prediction, right? So you can see that you largely reduce the variance term, right? So you have a same bias term, you have a largely small, or you have a much smaller variance term. You add them together, you end up with a much smaller total variance. That's the idea. That's where bagging helps. Any questions regarding this? Okay, yeah. But here I just want you to be aware. We're talking about an ideal case where you're assuming all those 10 decision trees are independent of each other. Of course, this is the best case, but you know, every time we train, we regenerate data set based on the original data set, right? So the learned decision trees are actually not totally dependent on each other. There are some correlations. So the critical strategy for banking is that you're gonna reduce the correlation between different trees. That's where the random forest, that's how the random forest is motivated. It tries to use some random strategy to reduce the correlations between different trees. Okay, let's go back to the slides. Oops. So, so this bias and variance decomposition explains or justifies why banking can help, right? But this is just based on the continuous task, right? Continuous regression task, right? Someone may ask, okay, for classification task, do we have the similar kind of bias and variance trade-off? The answer is yes, and this has already been done by pioneers in machine learning. So I'm not gonna cover this, but here, if you're interested, you can take a look at this paper published in 2 decades ago. But here, let us go back to look at this variance term. We mentioned, as we just analyzed, right? If all the decision trees in your bag are independent to each other, well, that's perfect. And your variance is reduced to 1 over square root of the number of the trees. But this is just the ideal case. Why? Because your training set are dependent on each other. Because every training set for each individual tree is resampled from original training set. There is some kind of overlapping. And imagine if your data have some kind of like dominant features or attributes. And every time, no matter how you resample those data sets, they are always selected to first do the split and then a second do another split with the second attribute and so on. So you can imagine all the trees will have like similar structures, right? So that the predictions will be highly correlated. In the extreme case, suppose those attributes are so powerful, so dominant such that no matter how you resample the training set, right, you create exactly the same tree. Do you have the 10 identical trees? Do we really reduce the variance? No, right? So if you have 10 random variables are the same random variable, your variance does not change at all. Okay. Then the problem is that how can we reduce the variance? Right? And how can we avoid this happening? Right? As we mentioned, right, we do not need to control the growth of the tree. You can grow the tree whatever large you want because we seek for small bias. Right? And we reduce the variance by averaging those strong classifiers. Right? So the problem is how do we reduce the correlation? So here is what the random forest comes from. Is kind of upgraded version of the common bagging trees. So the idea is that, okay, I'm gonna try my best to avoid those trees share similar attributes to split, share similar structures. How can we do that? At each step, right, we first draw a subset of available attributes. And then we only look at this subset, this random subset, and take the best one to split it. Like at each stage, for example, you might have at the second stage, you might have like 15 attributes in total, right? And if every tree I just follow the 15 attributes in total, it's likely that you can select the same attribute to split. But right now, for each tree, I'm going to first generate a subset of attributes. Like I sample 5 attributes out of these 15 available attributes. And then I always rank the attributes in this 5 subset. In this subset, including 5 attributes, and then I rank them and pick up the best one. Right? In this way, you can largely avoid the chance that, okay, tree 1 gets attribute 1 for the second split, and tree 2 gets attribute 1 for the second split as well, right? Because before we do the splitting, we first draw a subset of available attributes. So here's the algorithm details. So the whole framework is kind of the same as the baggage trees, right? And big T iterations, inside each big T, we can draw M examples. And here M is chosen, the size of the resampled data set is chosen to be the same as our data set, right? Uniform with replacement. You got X, T, Y, T. And then you call this new algorithm random tree learn to learn this entry CT, right? And finally, you will finish all the big T iterations. You got big T trees, you just vote of average according to the tasks. And then, how do we perform random tree learn? It's almost exactly the same as ID3, recursively partition data sets, select attributes, and to do split. But before we perform split, right, we first random sample a very small subset of the current available attribute set A, denoted by G. And then we just select best feature from G rather than from A to perform the split. And you can use information gain, you can use gene indexing, whatever. Once you identify the best attribute in G, and you can perform the split and grow the branches and then recursively call this algorithm. So you can see that at each step, right, for the same attribute set, even for the same attribute set, right, and different trees might select a different small range in A, right, and from which we select one best feature. Right? In this way, we can largely reduce the chance that two trees select the same attribute to split, and they're more likely to grow totally different trees. In this way, we can largely reduce the variance term so that to substantially improve the expected error. So, any question regarding this framework, this pseudocode? Yeah, let me emphasize again, right? When you implement your random forest in homework 2, just plug in one line of code. Before we calculate information gain for the attributes in the attribute set, right? We first perform a random selection. Random select a small range, a small subset of attributes from A. And then inside the small set of examples, you just calculate information gain around attributes and pick out the one to split. That's it. And this tiny multiplication can largely reduce the correlations of different trees in your bag and end up being very robust in practice. Any questions so far? Okay, great. So now we have finished the introduction of the ensemble learning. Okay. So we talked about boosting strategy, and I'll talk about another widely used strategy called bagging. Right? Although bagging is even more straightforward than boosting, it also performs very well, and it can be done in parallel. Right? And I hope everyone will be asked to implement your random queries. So just to be careful, how do you do a random tree learn procedure and plug in this code snippet, right? Random sample a subset of attributes each stage, at each node correctly, you see very good performance. Okay.